This conference will now be recorded.
Hello students, today we'll be discussing about superposition of principles.
This conference will now be recorded.
Hello students, we have been discussing OA optics, which is a chapter from 12th second part. So we have learned so far light is a wave. Okay, it behaves as a wave in certain phenomenon, interference, diffraction, polarization, etc. And we have learned what is called wavefront. Then so far we have learned Huygen's principle. Okay, principle, and we have applied Huygen's principle or Huygen's construction to explain the phenomena reflection and refraction of light. Even dispersion also can be explained with this construction. Okay, so these are the things we have already learned. So today what we are going to learn is very important and interesting topic, and this part will be really important for competitive exam like NEET, then iitjee and other exams. Okay, so let us learn this particular topic, principle of superposition of waves and interference of light. So we'll learn this very carefully and attentively. Let us start our discussions then. Okay, so see, what is superposition principle? So this principle, superposition principle, we have already learned 2 times. Superposition principle, okay, or principle of superposition. If you remember, in electrostatics, while calculating forces between or among multiple charges, right, at any point, electric field at any point due to multiple charges. So electrostatics, we have learned this principle, superposition principle. So this is similar to that, and also in wave motion, when we have seen superposition, that time also we have learned wave motion during discussions on the stationary waves and all. Okay, so we have already learned a little bit about this principle. See, in the electrostatics, what we had learned, I'll just recap so that you can understand this principle over here in the wave optics. Similar, okay, so suppose there are q1, q2, q3 and q4, etc. Okay, so I just want to calculate electrostatic force or Coulomb force on q1 due to all other. So that time what we had done, we had seen the forces individually. Okay, individual, okay, like each pair at a time, and when we calculate forces between each pair, we neglected the presence of all others, right? So we have thought like all charges, each point charge, they're independent of each other. Okay, independent of each other. This point you have to remember very well. So in that case, what we have got, the resultant force, we have got the vector sum of all like forces due to all others. Okay, so resultant force like 1, 2, then 1, 3 plus 1, 4. So all 3 forces we have taken, right? So this is what we have done. See what we have done. We have independently found out the forces between each pair. I'm just calculating electric force on this Q1 due to all other charges. So this is what it is. So resultant force was obtained by the vector sum of the forces calculated taking each pair independently. Okay. So when we calculated F1, 2, that means the forces between 1 and 2 charges, then we had neglected the presence of 4 and like Q4 and Q3 charges. Okay. So similarly, if when we calculate 1, 3, F1, 3, we had just considered the presence of Q1 and Q3 only and neglected the presence of others. So all other charges are independently existing, but we thought that they don't influence when we just take one pair, others will not interfere into that. So similar thing is here also. So look here, when multiple light wave, okay, at least more than one, two or more light wave passes through a medium, okay, see they are traveling in the same direction, and when they passes through a same point, when more than two waves, like more than one waves, two or more than two can be possible. So when they are traveling in a medium and eventually they meet at a point in the medium, then what happens? When means what we actually displacement term will use here. You know that y is equal to a sine omega t minus kx or kx minus omega t, kind of that we write, isn't it? So let us write plus. Okay, so you know this is displacement. This is the displacement of the medium particle medium. Okay, due to the wave. Okay, and this is the amplitude, maximum displacement of the particle. This is the phase term, we have learned that, okay, already in the wave motion. So each wave will actually produce some displacement. Okay, each wave will produce some displacement for this particle, and we'll treat these waves as independent waves. Okay, independent, so that when it comes here, see, suppose the wave number 1, wave number 2, wave number 3, these three waves, like see when this one passes through, maybe the displacement is y1, and when this one is passing through this point of the medium, it is producing displacement y2, and when y is passing through this, it is producing displacement y3. So resultant displacement will be similar to, see, the resultant displacement of this particle due to all other waves, all the waves superposing at the same point. Superposing means they are meeting at the same point, this P, let us say. Then the resultant displacement will be vector sum of the displacement produced by individual waves. Okay. So this is actually called superposition principle. So let us see that statement now. I'll come to this point again. Let us see the statement. According to the principle of superposition of waves, when a number of waves traveling through a medium superposing on each other, the resultant displacement at any point in the medium at any given instant is equal to the vector sum of the displacements produced by individual wave at that point. Okay, let me clear you this again once again. Suppose that there are n number of waves. Suppose n number of waves. Okay, n number or n waves. I'm writing n number. You have to understand that n means n number. Okay, n waves. N waves are superposing or meeting. Meeting means they are just falling at the same place. Okay, at any instant of time. This is called superposition. This is called meeting. Whatever you say, and we'll see a special term of superposition is interference. Okay, we'll see that. Waves are also n waves are superposing on each other at any point in the medium. Okay, at any point in the medium. All right, so at any point it is like n number of waves are superposing, and let us say individual waves produces displacement y1, y2, excuse me, there was some network issue. All right, so suppose there are n waves, they are superposing on each other at any instant of time at a point, and each individual wave produces displacement of y1, y2, y3, like that. Nth one produces y1 displacement. Okay, so then the resultant displacement will be vector sum of displacements produced by individual waves. Okay, so this is actually the meaning of this superposition principle. Okay, now see, when these waves they meet on each other or they superpose on each other, there could be, I hope you know the phase of wave. Okay, phase of wave. Okay, so okay, so I'm supposing you know this phase of wave. So when the waves are superposing on each other, then we need to check whether the waves are superposing in phase or out of phase. Okay, in phase or out of phase, there are two terms, in phase or out of phase. So what is in phase and what is out of phase? How do you understand whether the waves are superposing on, like superposing or meeting in phase or out of phase? We can do that. We can understand that by seeing the pattern of the wave. Let us see that. See, suppose there are two sinusoidal waves. See, I have taken, see here, there are two figures A and B. I have taken this figure now and discussing. So see the figure 2, figure A. So there are two waves. You can see that this one, number 1, and this is number 2. So when, okay, let me tell you once again for your convenience. So this is called crest C, and this is called trough. Crest means maximum amplitude and trough having minimum amplitude, and these are nodes, as you know, okay, where the displacement of the particles are 0 or medium is 0. Okay, so when you know, see, similarly I have in the second wave, this is the first wave, this is second wave, so I have crest as well here, trough, crest, trough, right here also crest and trough. Now when the two waves are meeting, having their positions of crest and trough at the same positions, see, the crest of the first one is at the same place where the crest is for the second wave, and the trough for the first wave is at the same position where the trough of the second one is, right? So like that, when the trough or crests, troughs or crests are meeting at the same position for the two waves, then we say that these two waves are in phase. Okay, in phase. These two waves are in phase. All right. So these two waves are called in phase. They are meeting in phase. Okay. Or they have the same phase. So this is what we can say. And when they are meeting in phase, then you know, see, the amplitude or the displacement will be additive. Okay, displacement or amplitudes of the waves will be additive. See, suppose for the first wave the amplitude is a1, and for the second wave the amplitude is a2. Then look, the amplitude has been additive. See, this is this much only, this is this much only, but resultant, this is a resultant one. Okay, resultant wave, resultant wave. Look, this resultant wave. So this resultant wave has greater intensity, sorry, greater displacement or greater amplitude. Obviously intensity, see, intensity, as I have uttered the term, let me tell you, intensity wave of wave is actually proportional to the square of the amplitude. So if the amplitude is more, then intensity will be more. If the amplitude is more, that means you know the displacement is also more. Okay, so resultant wave will be, actually see, the displacements will be additive simply. Okay, this additive, so their amplitudes are actually additive here. But if the waves are not meeting at phase, like in phase, see, in this case, see, I'll just show you one figure. Suppose one wave has this much, like this, okay, sinusoidal wave only, but some other wave, see, crest is happening here. So suppose this is wave 2, and this is wave 1. Look their position, see, that crests are not meeting at the same or not falling at the same position, whereas the amplitudes are same. Amplitudes may be the same, but they are not in phase. Okay, amplitudes are same but not in phase, they have some phase difference. Okay, now if this crest, see the figure B, at this place, you look, I have taken totally out of phase. Okay, so as I had shown you that if there is a displacement between the positions of the crests or troughs between the waves, then they are not in phase, they have some phase difference, but phase difference is 180 degree. See, 180 degree phase difference here. Phi is 180 degree, or totally these two waves are totally out of phase when at the position of crest of one, the trough of the other is falling. Okay, see here, this wave number one, see, this has crest at this particular position, whereas the wave 2 has the trough at this particular position. Now at this kind of, see, when the waves which are superposing on each other are meeting 180 degree out of phase, then their resultant amplitude will be a2 minus a1. There will be minus sign. Obviously, if these two are of equal amplitude, then resultant amplitude will be, or resultant displacement will be 0. Okay, resultant displacement will be 0, so intensity will be 0, everything will be 0. So I hope you have understood. Now see, in the superposition principle, so what we have seen so far, we have learned what is called superposition principle of waves, and then we have seen what happens when two waves superpose in phase and when two waves superpose out of phase. Okay, so in one case resultant intensity will be maximum, or resultant amplitude will be maximum. In other case, resultant amplitude or resultant intensity of the light will be minimum or 0. Okay, so these are the two cases. You can just look the figure now very well. Okay, so this is about principle of superposition. Now let me tell you, here actually we are going to discuss interference of light. So for the interference of light, we need to know what is called superposition of waves, because interference is some special kind of superposition. Okay, interference of light is special kind of superposition of light wave. We'll tell you what is that speciality. So see, to have superposition principle like interference of light, we need a special, see, any two wave, if they interfere, you cannot see interference of light. Okay, so that's why you need some special wave. Okay, special waves which will be interfering on each other. But what is that specialty, I'll tell you now. So see, sources of light will be producing light wave, right? Sources of light wave will produce light waves. So the sources of light waves should be coherent. So now I'll tell you what is called coherent and what is called incoherent sources of light, or incoherent not only for light, even interference happens for other waves like sound wave. Okay, so interference will happen when two waves are coherent wave. Okay, coherent waves. For having coherent waves, we need coherent sources of waves. So now I am discussing what is called coherent source and what is called incoherent source. Before I tell you these definitions, let me tell you something. interesting, and maybe that is like that can give you some concrete idea about coherent and incoherent sources. Suppose you have two needles, so these are actually needles. And suppose by some mechanism you can make these needles up and down vertically and periodically, okay, periodically up and down on the surface of water of a trough. This is trough of water, okay. In a trough of water, you just set this needle on the just on the surface, and by some mechanism, if you can make this move periodically up and down on the surface, then you know what will happen. I hope you can imagine the thing what will happen. So there will be waves produced by two point of impacts. See, these are point of impact. We have discussed the wavefronts, right? So these are two point of impacts, and at this point of impact the waves will start, like waves will produce, and that waves will be water waves will be progressing all direction in terms of circular patterns, okay, as you see here. All right, and suppose these two are okay, so now the waves produced in these 2 points will have certain phase relationship, a particular or definite phase relationship. That means, you know, if suppose one wave has phase phi 1, another one has phi 2, so they will have phase difference phi 2 minus phi 1, or take difference phi 1 minus phi 2, okay. So this phase difference will be there, and if this phase difference is maintained throughout their travel, if this phase difference is maintained, then these two waves will be called as coherent waves, and the sources are called coherent sources. So here there are two sources, S1 and S2. They will produce waves which will have definite or constant phase relationship. Suppose there is a point P over here. If suppose by this mechanism we are able to make these needles move up and down on the earth's surface simultaneously without any time gap or without any time difference between them, then what will happen? The waves produced by this S1 source and S2 sources will be having the same excuse me, will have the same phase. So when they have the same phase, and if suppose the waves starts sometime t is equal to t0, and the wave from S1 source reaches to this P after some time t, and also the waves produced by S2 reaching the point P at the same time t, then the path difference, because the waves in the medium will be having the same speed, so the path, see the path S1P and S2P will be the same, right? This will be same, okay, this path will be same, so there will be no path difference between the waves on reaching to this point P, is not it? They will travel the same amount of path, so they don't have path difference at all. So if there is no path difference, then they are called, they are in phase. They have maintained the constant phase relationship, because in the beginning they are produced at the same time and they are reaching also here at the same time. So that's why same time in the sense same, take the same duration of time to reach over here. So they don't have any time lag. So they don't have any path difference. Hence phase. See, path difference and phase difference has a relationship. See, phase difference, that is actually denoted by delta phi. Okay. So this path difference is actually denoted by lambda. Sorry. That is denoted by delta. Path difference is denoted by delta. Okay. So here path difference is 0, right? S1p minus S2p. S1p minus S2p, or I'll take difference in between. So path difference is denoted by delta and phase difference is denoted by del phi. Okay, del phi. So path difference is related to phase difference. How? It is defined as phase difference is equal to 2 pi by lambda. Lambda is the wavelength of the wave into delta. Delta is the path difference. So phase difference is 2 pi by lambda into path difference. Okay, path difference. This is the relationship. Okay. So this is relationship between phase difference delta phi and path difference delta. All right. So what I was going to discuss, what is called coherent source. So when two sources, okay, two sources which emanate light waves of same frequency or wavelength, see, the two sources should produce same frequency of like waves of same frequency. Two sources which emanate light waves of same frequency with 0 or a constant phase difference. See, or phase difference may not be 0. There should be phase difference, but that phase difference should not change randomly. If suppose the phase for the wave 1 is changing to some phi 1 plus some x, the other one also should change to phi 2 plus x only. Okay, so that the change is same. Okay, so that the change is same and ultimately phase difference will be 0. So phase difference can be either 0 or constant all over the time or all over the spaces. Okay, and the wave travels. So two sources which emanate lights of same wavelength or frequency with 0 or constant phase difference between them are called coherent sources. For example, laser source. Okay, laser sources, they are actually highly coherent sources. Highly coherent sources, they produce, laser sources produce very coherent light. Okay, coherent sources of light are laser sources. Okay, you can remember this example. Now incoherent, now see, coherent, there will be constant phase relationship or there will be no phase difference randomly, like no phase changes randomly. But in this case, those things will be happening. The sources of light which do not emanate light or waves with constant phase difference or with a constant phase relationship are called incoherent sources. In this case, actually phase changes randomly with time or space. Okay, phase changes randomly as the wave progresses. Okay, so this is about coherent source and incoherent source. Now we'll see how to produce, or see, incoherent sources. See, whatever sources of light you see in the nature, okay, naturally whatever you see are actually incoherent sources of light. Okay, let's see, a bulb produce two bulbs. You keep two bulbs separately, light, like switch on them, the light waves they produce will be incoherent. Two tubes, sun rays, etc., these are all actually incoherent sources of light. Okay, when two sources do not produce waves with constant phase relationship are called incoherent sources. Like any two separate bulbs are called incoherent sources of light. Okay. Now we have learned that we need a coherent source of light which will produce coherent waves to exhibit the phenomenon of interference of light. Now, how to produce coherent sources? So there are different ways to produce coherent sources. And we can actually will be seeing Young's modulus, Young's double slit method. So since Young's word came, so by default modulus has come from my mouth anyway. Please do not mind. So Young's double slit method. Young's double slit method will see, suppose you have a single source of light, okay, and this light itself is taken, to make two sources. Then see, this is S1, S2. These two sources are called coherent sources because whatever changes happens in this source of light, original source of light, the light coming out from here also will have the same changes of phase. So these two will have a constant phase relationship. Okay, so this is called double slit arrangement, Young's double slit arrangement. Very simple. This is actually a talented guy who had done a lot of things in the wave optics in the beginning. Okay, in the starting phase. Okay, so this was actually a remarkable experiment done in the laboratory, but with very simple arrangement of experimental arrangement. Okay, this is really remarkable. Okay, so another way of producing coherent sources are called, so this is sometimes called YDS. Okay, Young's double slit arrangement, YDS arrangement. The Fresnel's biprism, Lloyd's mirror. So these things are not included in your syllabus. I'm not going to discuss that. Only thing we'll discuss is this one, Young's double slit arrangement, and how interference phenomenon can be produced, or interference can be produced by Young's double slit experimental arrangement. We'll just discuss that. Not today. We'll discuss that in the next class. Today, what we'll do, we'll just define what is called interference of light and what are the conditions of different types of interference to occur. Okay, those things we'll be discussing. So two sources must emanate monochromatic light. Okay, so these are conditions actually. So if the two sources of light are obtained from the same source, same original source, as I said in the YDS, so that those two sources can be coherent sources, and these coherent sources must be having the same monochromatic, means chrome means color. Okay, chrome means color. Chrome word is coming from the concept of color. Okay, so color, chromatic, monochromatic means mono means one, so one light, one wavelength should be there, or same wavelength. Okay, so light waves which are treated as coherent sources will have the same wavelength. Then path difference between the waves arriving the screen from the two sources must not be large. It should not. See, path difference, as I said, phase difference is equal to 2 pi by lambda into path difference delta. But this path difference also has a limit. If it is becoming more than 30 centimeter, then the sources cannot be coherent. Okay, and interference cannot happen actually. See, if you have, okay, now let us discuss what is called interference of light. See, interference of light is actually very remarkable and very beautiful phenomena. Okay, of light. You know, because of interference, we see multiple colors. Where? On the butterflies. Okay, butterflies, and then peacock feathers, peacock feathers. Okay, even in the soap bubble also we see some colors, right? Soap bubble. Here whatever colors we see and whatever phenomenon we see having multiple color, most of them are actually coming from the interference of light. Interference of light. So in the nature we see beautiful color, beautiful combination of colors due to this interference phenomena of light. Okay, so a combination like beautiful color combination or we see in the nature due to interference of light. So what is interference of light? Let us see the definition. When two coherent light waves traveling in the same direction superpose on each other, the intensity gets redistributed in the region of superposition, exhibiting maximum intensity or maximum brightness at some points and minimum intensity or darkness at some other points. This splendid natural phenomenon of light is called interference. So as I said, interference is obtained or interference happens when two or more than two waves they superpose on each other. Okay, when they superpose on each other, at the point of superposition what will happen, even though suppose this wave has intensity I1, this has intensity I2, so this intensity of light at this particular position will not be same as I1 or I2. It will be different. Okay, so at this point there will be some point. So at this region of superposition, since wave is delocalized, so they will be meeting in a region. So in a region of superposition of this light, coherent lights, these are having same lambda and having constant phase difference, then they are called coherent sources. So coherent waves. So these coherent waves upon superposition at any region of space, so there will be some places where there will be maximum intensity of light and some places there will be minimum intensity of light. Some places there will be maximum intensity of light and at some places there will be minimum intensity of light. That means some places it will be bright, some places it will be dark. Bright, so I'll write bright, B for bright and D for dark. Okay, so this alternating or alternative bright and dark, these phenomena, beautiful phenomena will be able to see. Okay, this is actually called interference. Okay, I hope you have understood that intensity at the point of interference or in the region of interference, at some point intensity of the light will be maximum, at some point it will be minimum, not as the intensity of the incoming waves or superposing wave. The intensity will be totally different. Okay, not equal to I1, neither it is equal to I2, but it is something different. We'll just derive that expression for that. Okay, if I know the intensity between the intensity of each wave at the superposition, it depends obviously on the phase, how they are in what is the phase difference between them. We have to depend on that. So but the main thing is that because of interference there will be bright region and some places there will be dark region. See, bright region is fine, but how is it possible that two light was superposed on each other but they produces darkness? So light will show you something, but why will that make darkness? Okay, light and darkness. See, darkness. So this is something which is really very interesting to have this information that light waves upon superposition can create even darkness. Okay, is not it very very interesting or very much like exceptional thing that two lights they can produce darkness? So how is it possible? This is not simply superposition or not just simple addition or subtraction. Actually, obviously there is something else in this also. Okay, so why I was trying to tell you that interference happens when there are two waves at least, and waves are coherent, and upon superposition, the region of superposition, there will be brightness and darkness. Some places there will be maximum intensity, at some other places it will be having minimum intensity. Okay, intensity of light. This phenomenon is called actually the interference of light. Now there are two types of interference. Okay, there are two types of interference. As I said, the region where this brightness or maximum intensity is being obtained is called this interference is called constructive interference. Okay, constructive. So there are two types of interference. One is constructive interference and other one is destructive interference. Okay, so what is constructive interference? We will see when two waves interfere in phase. As I said, see, when they interfere in phase, the intensity will be maximum because this is additive. Okay, additive. Constructive interference, when they will meet in or interfere in phase, then the maximum. Okay, so then the resultant intensity becomes maximum. Intensity is directly proportional to amplitude. So when two coherent waves interfere in phase, then the resultant intensity is maximum, becoming maximum. The type of interference, this type of interference is called constructive interference. So as I said, in simple language, where there is brightness or two waves interfere in phase are called in phase, then intensity upon interfering would be maximum. So that is actually called constructive interference. That means light plus light, they will produce light with brightness, like intensity, increased intensity and brightness. Okay, but destructive interference means, you know, light plus light is darkness. Okay, darkness, or they produce minimum intensity. So destructive interference is when two coherent waves interfere in opposite phase. Then opposite phase means what? I have already told you. Opposite phase means tau of one wave is actually meeting at the position of tau of that of wave. Okay, so this is tau and this is crest. So this is actually called, okay, so these waves are called or said to be out of phase. Okay, so when two coherent waves interfere in opposite phase, then the resultant intensity which is proportional to the square of the amplitude okay, so resultant amplitude will be 0 or minimum. You have to understand in place of destructive interference. Now we'll see the conditions for getting constructive interference and destructive interference. So for that, we'll just do a little bit of calculations, not calculations, some short derivation. Suppose there are two waves, y1. Okay, I'm just taking two waves. One is y1 is equal to a1 sine omega t. Okay, so this is amplitude of the first wave, this is the displacement term, and the second wave has displacement y2, like it can produce y2 displacement at particular position. It has amplitude a2, and this has some phase difference omega t plus phi. Now, by the law of superposition of principle, what we know? By the law of superposition or by the superposition principle, what we know, the resultant displacement will be sum of vector sum. Here, since I am not writing vector, so this is also scalar. So this is actually according to principle of superposition. Okay. Now what is this y1, y2? Let me write them. A1 sine A2 sine omega t plus phi. Now this term we can actually use the identity from trigonometry. See trigonometric identities we can simplify like this: a1 sine omega t, a2. See this term sine a plus b. So sine a sine b plus cos a cos b. Actually sine a cos b, it is sine omega t I'm sorry, this is let me write in bracket. So this is on this side equal to so now see sine omega t here. Okay. Now I'll actually write this elaborately. So y is equal to what we get? Ultimately, we get a1 sine omega t plus a2 sine omega t cos phi then another term a2 cos omega t sine phi. Okay. Now see these two we can take common actually. Let me write this as a sine phi because sine phi is not time varying, so that can be a constant term. A2 sine phi. So look here, this term if I just consider something and this term if I consider something, then maybe I can simplify the equation further better, and I will do that. So let us consider a1 plus a2 cos of phi. This is equal to so this is with sine, right? So I'll take this as cos of theta and this term as a2 sine phi. Okay, this, let us say this is, I think here we have to take this as a cos theta, maybe, yes, a cos theta a2 sine phi. Let us take that a excuse me, sine of theta, sine of theta, sorry. Now if we just write them here, simplify this. So what you can do is you can do this. I'm just writing it. See, okay, let me just complete that. Because of sine theta, okay, fine. This is sine omega t, sine omega t cos del cos theta, cos omega t. Okay, so what we can do is we can, I'm just writing this writing this question itself, otherwise it will take time. You can just go and do it with full brain. To sine omega t a cos of theta plus this we have taken as a sine theta, so cos omega t, the cos omega t, a is common, cos omega t sine theta. So this will give you actually a nice one. See, omega t plus theta. So this is how, see, we have seen the interfering waves were sinusoidal, and this is also sinusoidal. Okay, this is also sinusoidal. This is the resultant wave we get upon superposition. But what is this theta and what is a? So that we have to actually find out from here. So at least a we can find out. We'll just square them out. This guys. So a cos theta whole square. That means a1 plus a2 cos phi whole square. So we will actually do one thing. We will just add them up. We'll okay. So what we get here is, say, intensity A will be obtained as, see, A1 plus A2 cos of phi whole square plus A2 sin phi whole square, right? So as we have taken from here, so A, I have to find out what is A. Okay, this is the resultant wave we have got. Now we have to find out what is A. So if you just do this, what you get? You get A1 square plus A2 square. Okay, A1 square plus A2 square, and then 2 A1 A2 cos phi. So this is what you get, right? So look here, actually after superposition also the waves will be of same nature, like this, same nature. But the problem is this intensity or the amplitude. See, the amplitude of the interfering like resultant wave is becoming this. This is actually amplitude now. Okay, this is the amplitude. Okay, I'm sorry, this is square root of this. This is amplitude. Now what will be the intensity? Intensity is actually directly proportional to the amplitude square. So we'll get, in terms of intensity, if we write, then we have to square this up. Let us say proportional to constant k, and here all the proportional to constant I am taking as k both sides. So this will k a1 square plus k a2 square. So a1 square is the intensity of the light source 1, a2 square is the intensity of light source, coherent source, second source. Okay, like here I have taken the light wave. This is from first source, this is for second source. Okay, so what we get here, ka1 square into square root of k a2 square cos phi. See, this I can write as the whole intensity. This I can write I1. This I can write I2 plus, see, this part is actually root over I 1, and this term is root over I2. So inside the square, and this is square root. Okay, so this is actually the total amplitude. So after interference, so what is, or after superposition, what is the intensity of the light at the position of superposition? That is given by I1 square plus I2 square plus square root of I1 I2 cos phi. This is actually, and this particular term, you can see this interference term, this particular term, this where I1 and I2 both are there as a multiplication, this is actually giving you the interference. Okay, this is, see, these are actually producing general illumination. That means everywhere the intensity of light will be same everywhere. Okay, general illumination means, but this term will produce interference. That means it will actually produce darkness and brightness at places, different places, darkness, brightness alternatively. This is actually giving you the interference. Okay, interference. So this product term, okay, square root, like 2 into square root of I1 I2 cos phi. This is actually the term which is called interference. This gives the interference, okay? Interference. This gives the interference, okay? So I think I'll just stop it here. Next day I'll tell you like what are the conditions for constructive interference and destructive interference. Okay, I hope this so far we have understood all. Okay, so I'll stop it here for today. Thank you for your patience. Bye for today.